In this screencast, I'm going to walk you through the solutions to the three related rate problems that we worked in class on Friday. The first was number 24 and involved a train traveling away from a point A. So there's point A, train's moving to the east, and the distance between point A and the train is given by x. There's a camera that's located to the south of point A, and I labeled that with point C, and I said that that distance is 0.5 kilometers. That was given to us in the problem. And then I drew in a dotted line, which is the distance between the camera and the train. They tell us in the problem that the speed of the train is constant and is 0.8 kilometers per minute. And so I wrote that as dx dt, which is the speed of the train, 0.8 kilometers per minute. Okay, in part A, they asked us to find z in terms of x. And what I do here is look at the picture that I've drawn for the problem and think about the relationship, the geometry of the problem. What is the relationship between x, 0.5, and z? Well, I have a right triangle here, right? And so I know that the Pythagorean formula holds, so that I can write 0.5 squared, which is this side length, plus x squared, which is that side length, is all equal to the hypotenuse length squared, z squared, which is that guy. And the only last step I need to do for part A is to solve this for z in terms of x. And that just involves taking the square root of both sides. As kind of a little aside here, when you do the square root, mathematically speaking, you should really be putting a plus or minus in front of the square root sign because that root might be positive or negative. But in an applied problem like this, we know that z, this distance between the camera and the train, is always positive. So I'm going to eliminate the negative root there and just write the positive one. In part B, I'm asked to figure out how fast is the distance between the camera and the train changing at a particular moment in time. And they tell us that we're interested in when the train is 1 kilometer from the camera. And so the first thing I'm going to do is notice that I'm still using this Pythagorean formula relationship, except now instead of having functions x and z, I need rates like dx dt and dz dt. So I can take the equation that I have in part A and differentiate it with respect to time. When I do that, right, this first term, 0.5 squared, that's a constant, so its derivative is 0, that disappears. X squared turns into 2x dx dt, and that's all equal to the derivative of z squared, which is 2z dz dt. Alright, in order to solve this equation now for dz dt, the quantity I'm interested in, I need to know several things. I need to know what x is, what dx dt is, and what z is at the particular moment in time that we're talking about. So I wrote off to the side here that when z is equal to 1, I know that this equation is true. That's another Pythagorean formula. 0.5 squared plus x squared is equal to 1 squared. And I can solve that equation for x, and I got 0.866 kilometers. So what that means is when the train is 1 kilometer from the camera, it's 0.866 kilometers from point A. Alright, so come back down here, look at my related rate equation, and I'm going to start plugging in the things that I know. So I've got 2, and there's x, which is 0.866. dx dt is given to me in the problem, that's 0.8. I've got the 2, and I've got z is equal to 1, and then dz dt, which is the thing I'm trying to solve for, tacked on the end. I'm going to solve this equation for dz dt by dividing both sides by 2, and then doing this arithmetic gives me that dz dt is 0.693 kilometers per minute. So the interpretation here is that when the train is 1 kilometer from the camera, the rate at which that distance is changing is 0.693 kilometers per minute. If the train had been at a different distance from the camera, then this rate will be different, because that rate depends on x, dx, dt, and z. So you might want to think about other situations here, or how you could expand this result for different things. But anyway, let's go on to part C. In part C, now I'm interested in the angle that the camera is rotating at in order to stay focused on the train. Well, if I'm interested in an angle, I need to go back to my picture and tell you exactly what angle it is I'm interested in. And what I've done here is labeled this angle between sides AC and TC with a theta. Because if I think about it, right, the camera, if it's pointing directly at point A, I'm calling that an angle of 0. And then as the train moves to the east, this angle theta is going to grow. It's going to get bigger and bigger and bigger. And if you think about it, here's a little thought experiment. What happens to theta as the train gets further and further away? In other words, what I'm asking you to do is take the limit as x goes to infinity and figure out what theta is. What would that angle theta be when x approaches infinity? Alright, so that's a thought experiment for you, but let's get back to the problem. So I need a relationship between theta, x, and z. Well, again, I look at the geometry of the problem here, and I remember from either pre-calculus or a trig class that the sine of theta is opposite over hypotenuse. So I've got the sine of theta is equal to x over z. Alright, now let me scroll down a little bit here to show you the rest of the problem. Unfortunately, the picture is going to be lost. Sine of theta is equal to x over z. Now, what I'm going to have to do is differentiate this with respect to time. And so a little shortcut that I'm taking here is I'm going to multiply both sides by z, which is totally valid, but it's going to avoid me having to do the quotient rule on x and z. And that's just my own personal preference. If you want to do the quotient rule, feel free. But I'm going to move that z over here to the sine multiplied by sine theta, so I don't have to deal with the quotient rule. Alright, and I also put a little note in here as kind of a reminder in red. Z, as written in this equation, really represents z of t. It's a function of time. That distance is changing, as is theta, as is x. So I've got three different quantities in this equation that are changing in time. Alright, now let's go ahead and differentiate with respect to time. To do that, I'm going to need a product rule on z and sine theta. So here's z times the derivative of sine theta, which is just cosine theta d theta dt. And I add to that sine theta times the derivative of z with respect to time, which is dz dt. And that's all equal to dx dt. Now, when z is equal to 1, I already know that x is equal to 0.866, right? I figured that out in part B, I think. But because I'm dealing with theta here, I'm going to have to figure out what the sine of theta is and what the cosine of theta is at the particular instant in time when z is equal to 1. So, sine of theta, right, that's opposite over hypotenuse. So that's just going to be 0.866 divided by 1, and I just wrote that as 0.866. Cosine of theta, it's adjacent over hypotenuse, so I just wrote that as 0.5. And now I'm going to plug in all that information. So z is 1, cosine theta is 0.5, d theta dt, that's what I'm looking for. I'm going to add the sine of theta, 0.866, dz dt is 0.693, dx dt is 0.8. And so after I plug in all of those numbers, I can solve the equation for d theta dt. And doing arithmetic, I get 0.3997 radians per minute. And that's how fast the camera is rotating in order to stay focused on the train. All right, let's take a look at the next problem, number 18. What's going on in this problem is you have a cone filter that you might find in a coffee maker, and that cone is filled with water, and we're going to let some water drip out of it and figure out how fast the height is changing. But what they ask in part A is how long it's going to take for the water to completely drain from the cone. All right, well, I need to know the volume of a cone, right? That's pi over 3 r squared h. And I can figure out how much water I have when the cone is completely full by plugging in the numbers for r and h that were given to me in the problem, so 6 and 10 centimeters. When I do that, I get that the total volume of water in the cone is 376.99 cubic centimeters. I'm also told in the problem that water leaves the cone at a rate of 1.5 cubic centimeters per second. And so the way I expressed that was I said dV dt, the rate of change of volume with respect to time, is equal to negative, because water is leaving the cone, right? V is decreasing, negative 1.5 cubic centimeters per second. All right, well, if I know the total volume of water and the rate at which it leaves, it's pretty simple division to just tell you how long it takes that the water to completely leave, all the water to leave the cone. That's 251.33 seconds. Now, in part B, we are kind of at a moment in time where part of the cone is filled with water and part of it has left, and we're interested in finding how fast the height is changing. So what I've drawn here is kind of a cross-section of the cone, illustrating how we're going to figure out how to get h in terms of r, or vice versa, r in terms of h. So I've got similar triangles here. I can write h is to 10 as r is to 6. Simplifying that, I get this relationship between h and r. I've got my volume equation for the cone. I'm going to replace r with 3h over 5. That comes from solving this equation for r. And now doing a little bit of arithmetic, I get my volume all in terms of h. So volume is 3 pi h cubed over 25. That's part B. And in part C, they ask me to find how fast is the height changing when the height is 8 centimeters. Well, luckily, I've got this volume equation right here in terms of only h, so I can differentiate with respect to time, dV dt on the left. I've got 3 pi over 25, and then in here, in parentheses, I've got the result of taking the derivative of h cubed with respect to time. So there's just a little power rule there that gives me 3h squared, and then a dH dt pops out because, remember, h is a function of time. Now, plugging in some numbers that I'm given, I know that the volume is changing at negative 1.5. That's that rate. There's my 3 pi over 25. There's 3. They tell me when h is 8 centimeters, so I'm plugging in 8 for h. And dH dt is the thing I'm looking for, so I'm going to leave it as dH dt in the equation. Solve this guy for dH dt, and I end up with negative 0.0207 or 0.0207 centimeters per second. So this makes sense. The sign makes sense. H is decreasing as the water leaves the cone. So that takes care of that problem. Let's go on to the next one, number 20. In number 20, you have an oil slick that's spreading. And so they tell you that the oil slick is circular with radius r, and they ask you how fast is the area of the oil slick changing when the radius is 150 meters. Well, the first thing I do is I find the relationship between the area of a circle and its radius. That's just pi r squared. Take the derivative with respect to time. So I've got a dA dt is equal to 2 pi r dr dt. And then all I got to do is plug in 150 for r and 0.1 for dr dt. Both of those were given to me in the problem. And when I do that arithmetic, I get 94.248 meters per minute, or if I kept it in terms of pi, that's just 30 pi meters per minute. And that's, again, that's how fast the area of the oil slick is changing with respect to time when the radius is 150 meters. Now, in part B, now we're looking at not only the surface area of the oil slick, but the volume of the oil slick. And they tell us in the problem that the volume of the oil slick can be modeled by a right circular cylinder. So here I've got a little picture of a right circular cylinder with radius r and height h. And I remember that the volume of a right circular cylinder is just pi r squared h. Now, they're going to ask us to find how quickly the height is changing for a given radius. And I hope that you can see that if you keep the volume of the right circular cylinder constant, if r increases, h must be decreasing in order to keep that volume constant. Let me say that again. In order to keep the volume of the right circular cylinder constant, if r is increasing, h has to be decreasing. Okay, so we'll start off with the volume of a right circular cylinder. We'll differentiate with respect to time. So we've got dv dt on the left. There's pi. And now, look what I've got here. I've got r squared h. Both r and h are functions of time. They're changing as time goes on. So because I have a product of two functions of time, I need a product rule. So I've got pi, that's just my constant. Then I have r squared times the derivative of h with respect to time, plus, and then h times the derivative of r squared, which gives me a 2r dr dt. Okay, now let's plug in some things that we know. We know that the volume of the oil slick is constant and that the derivative of a constant is 0. So dv dt has to equal 0. There's pi. Our radius is 150. That's given to us in the problem. dh dt is what we're looking to find. H is 0.02. 2, and then the radius again is 150, and then dr dt given to us in the problem as being 0.1. If I do a little bit of arithmetic here, a little bit of algebra, and solve for dh dt, I get that dh dt is negative 8.488 times 10 to the negative 6th meters per minute. And if I wanted to play around with this, I suppose I could put it in something like centimeters or millimeters or what other unit you want. But I'm totally fine just leaving this as a number in scientific notation and then leaving the units as meters per minute. And that takes care of the 3 problems that we worked on Friday.